Okay. So good afternoon. Still miss a few people here. So in general, Thursday is going to be a recitation or exercise given by Noga, as you know. I mean, and as I said, in principle, the exercises are very important. I mean, this is, as far as I'm concerned, you cannot really internalize this material or understand it without using it. And we also are going to have some programming exercise. I mean, all of us should be able to do some software. I mean, it can be in MATLAB or in any other language if you prefer. And Noga will tell you more about it, I suppose, at some point. And many of the things that we are saying here don't mean anything until you actually apply them and see that they really work. So we started to talk yesterday, after this long introduction, about the origin of probability theory and what we actually expect from probabilities. And I really mean that some of you at least will try to investigate this a little further. Maybe you should put on the web page the paper of Cox, which I think is really nice, but it's only a very small part of this domain of trying to axiomatize from the mathematical point of view the theory of probability, which actually has many different approaches. But for us, what is really important is to understand that it's an extension of logic. It's more or less a unique extension of logic as far as we're concerned. There are no other ways of thinking about it. And we can really use it as a foundation for theory of decision-making, theory of learning, theory of behavior, theory of cognition in general. And this is really why it is so important for both people who are trying to mimic intelligence wherever. I mean, artificial intelligence, learning, whatever. I really believe that everything is based on dealing mathematically with uncertainties in some fundamental way. And at the same time, it's really important for those who are interested in the brain, because in some sense, I think we can say today very clearly, our brain, not only our brain, any brain, is some sort of probabilistic, or maybe more generally, information processing machine, which is based on what we believe are the foundations of the mathematical foundations of uncertainty. And that's why it's important for anyone who really want to study. So, you know, and of course, it's not only a model of the brain in some sense. It's also the key, and essentially most of this course is really about using probabilities, using statistical inference, using algorithms which are eventually have this dual meaning. I mean, both as data analysis tools. I mean, this is what you are going to use if you want to analyze data in the world, and not necessarily in biology, anywhere. So it has, as we call it, I mean, it's a methodological tool. I mean, it's a method that you're using for analyzing quantitatively data. At the same time, in the context of brain science or computational neuroscience, it has the value of a model of the system you're studying, because the brain is actually doing data analysis all the time. So you really need to think about it in what philosophy of science calls both epistemological level and ontological level. I mean, it's both a model of your system and a tool for studying it. This is actually something very simple, very important about the brain itself. I mean, it's a machine. It's a machine that's generating everything we can do, including analyzing the brain. It's interesting in some sense. I mean, it's a machine that studies itself. But so the methods really have these two values, and everything we're going to say in this course has to be treated as such. So again, for those of you who are not terribly familiar with probability theory, Actually, I find that even those who studied formal probability theory often don't have a good intuition about it. And it takes actually much longer to really develop good intuition, and that's one of the things I want you all to have. So essentially, when you're not sure about something, remember this picture. There is the sample space, omega. You can think about it as the unit square, and think about the probability measure as the area. And usually, when you think about an event as some sort of a subset, or a subset of this set, you don't quite remember what do I mean by conditional probability, or what do I mean by the probability of union of events or the intersection of events. So think about it in terms of set theory, and remember that this usually you're right. I mean, this intuition that comes from thinking about areas in this space are usually it's usually the correct intuition. And then I said, okay, so if we don't remember exactly how conditional probability is defined, I think again, okay, we know that B is certain, and so it's the intersection of A with B and so on and so forth, divided by the area of B. And again, all the mathematical difficulties that come with this problem. So I'm talking not about all the possible subsets, but I'm talking about all those measurable subsets, all those things that I can actually assign measure to, area to. And those of you who can't quite think about sets in the unit square which don't have a measurable area are right about it. I mean, it's really very, very non-intuitive, but such things exist. So we actually talk about the field of all possible subsets of omega, which can be made out of intersections or unions of little squares, of pixels, if you want. And for those of you who come from computer science, really don't worry about continuity or non-countable things at all. But it's actually quite interesting to think about them, because the world is probably a little more interesting there. But anyway, so instead, one thing I wanted just to correct, I said 2 to the omega as the sets of all possible events in my sample space. It's actually not 2 to the omega. It's something which we call the sigma field, or the sigma algebra, that is made out of all possible countable intersections and unions and complements of sets which we call the basic measurable sets, which are on the line are simple intervals, if we talk about Lebesgue measure, and in the plane are products of intervals, which are little squares, if you want. Okay, so this is just to complete this little picture. The other thing you have to remember is this notion of randomness. Random samples, which is crucial for understanding anything we do about probability. And essentially, for those really who want some intuition, you have to think about the ability to randomly sample the square in uniform distribution around the square. Uniform, I mean, every little piece has a chance of being sampled, which is proportional to its area. Okay, so this is essentially all you need to know about sampling. And then people asked me yesterday, what do I really mean by random? A random number, a random sequence? This is actually a very deep question. So we take it here more or less for granted. There is an access. We have access to random numbers. One way or another, actually, it's enough to think about random bits. So it's enough to think about coin flips, if you want. So if I have anywhere a coin which can give you up or down or tree or poly or whatever you want to call it, head or tail, which in random, which is in a way, this is good enough, because again I can flip it many times and generate any number that I want in principle, including real numbers. And when I can generate real numbers in uniform distribution, I can, from real numbers in uniform distribution, I can generate any other distribution, as you might have seen, including Gaussian, including whatever you want. So, but the real question, what do you mean by randomness, is actually a little deeper, and we'll come to it later in the course. Essentially, random numbers for me, a source of randomness is something which I cannot predict. So it's enough for me, this coin flip is unpredictable in the sense that I don't have access to the actual the initial conditions of the coin, or the friction, or the air affecting it. So the physics of the coin flip is actually very simple. I mean, it's deterministic as far as we understand. But since I don't know the initial conditions exactly, or I don't have control of everything that happens to it on the way, due to what we call chaos, essentially. I mean, so very small change of the initial condition can change the head or tail, the flip of the coin completely. So for me, this is an unpredictable process. And once it's unpredictable, then it's not, I can take it as random. Of course, there's the deeper question, the philosophical question, is there true randomness in nature? And the answer to this, yes, we believe that quantum mechanical processes are random in some really fundamental way, which means that they are not predictable by anything, including God. So they're really unpredictable. So, okay, but you don't really need to believe that such things exist. And actually, it used to be, I mean, it's really unpredictable. And the question is whether we really need this true randomness or not. It's really not really very important. It's enough that we know that we cannot predict it in order to play with it in random, as a random source. And actually, pseudo-random numbers, those that you generate with the computers, are obviously not random, because they're usually deterministic in the sense if I repeat the same seed exactly, I get the same sequence. Actually very important that I can do it, that I can really debug my problem with exactly the same sequence of random numbers. And if I'm very smart, that I can actually decipher or break this machine and understand the rule, or maybe know the rule, how these numbers are generated, then they're of course predictable for me. But if the thing that you're trying to test, or you want to assume that this is a random number for you, is actually capable of predicting it, then you can actually show that then for this it's not random. It's really, so let's say I'm doing an experiment on a monkey, and I'm trying to randomize, I don't know, some image that the monkey is supposed to respond to, but the monkey is smart enough to predict what's going to be the next image, then the whole idea of random images is wrong for this monkey. So it's really random with respect to my computation power. How strong is my ability to predict the sequence? And if I'm a stupid machine, or have a limited memory, or have limited computation power, even a very simple generator of pseudo-randomness can act like random numbers for me. And this is precisely where pseudo-random numbers really work. Anyway, for us, this is just this intuitive idea of throwing independently, which means that points that don't affect each other, points on this plane, and generate things which are going to be eventually proportional to the area. And that's essentially everything you need to know. I mean, properties of sets, intersections, unions, and complements of sets, and this idea of sampling. And this is the key and the basic and the foundation of what we call probability theory today. All right. So I started to talk about statistical decision theory. And in fact, what we are really going to confine ourselves very quickly is what people call Bayesian decision theory, and I'll show you in a second what we mean by this. And so we have essentially several components, formal components, that we wanted to mention. So we write it as some sort of a tuple like this. I mean, what are the objects? So the first one was omega, which was state of the world. See, I should write it right down. So this is state of the world. So this is a random variable, and W, or belong to omega, is a random variable, which means I don't know it in advance, and it can be anything that comes from some distribution. Usually I assume that omega at this point is a finite set, or even just a binary set, like rain, no rain, or things like this. There was something which we call observation. The observations are so x belongs to x is some observation. This is a very general and very tricky thing. I mean, what do you mean by observation? So I gave the example yesterday of looking outside the window and see if it's cloudy or not. And in general, it can be a discrete thing, like cloud, no cloud, or a continuous thing. I can measure the temperature. Or it can be multidimensional. I can measure both the temperature and the cloud and the humidity and I don't know what, and the pressure. I mean, I can have a multidimensional set of observations. Some of them can have finite values. Some of them can continuous values. Some of them can have imaginary values. So it can be symbolic or discrete, continuous, discrete, whatever. Okay. So I write it with a line underneath, which means that in general this will be a vector quantity. Okay. Now, we're also going to assume very soon that we can make many measurements. So I can repeat my measurements many times, independently or not independently, and so on. The third component here was, if you want, I just want to be in the same order that I did yesterday. So we usually call them the action space. So little alpha belongs to A is actions or things that on which I'm essentially going to decide. So my algorithm is supposed to tell me how to choose the best possible action given my observation. So this is the next component here. And then I said something, maybe not in this order, which was what? The cost, right. So what is another quantity, which you usually denote by lambda. So lambda, which was a function of my action and the state of the world. So as I said, I usually write it as a condition on the state of the world, but you can, in the notes of Amir or many other places, it's written as just a function of these two variables. And this is the cost, so this belongs to this lambda, and it's the cost of action alpha at state W or omega. Okay? So in the example we gave yesterday, it's how much I estimate the cost of being without an umbrella in the rain, or how much I estimate the cost of carrying an umbrella without the rain, or something like this. Yes? Well, so at this point, all I say is that this is real number. It can be positive or negative.
Negative, not in the sense that you always mention that you took an umbrella when it's not raining.
No. It can be a positive cost or negative cost in the sense that I can think of, I can think about it as value or as a reward. I mean, actually winning something. So it can have, getting money, getting salary. It can be a negative or positive cost, but we usually think about it, not right now, we think about it as something we want to minimize. Something you want to minimize, which means I want a minimal cost. If you want to call it a reward or salary or money or value, then you actually want to maximize it. But I think you all understand that this is just a matter of sign. So minimizing the cost is maximizing the value. But at this point, I don't make a distinction between these two things. Okay? Later on, we may want to make a little distinction between cost and value. But then there were two other things here. So we have these four components, which are physical things in some sense. They belong to the world. Properties of the world, properties of what I can observe in the world, actions, which are things that I do or make a decision, and functions, the cost of my actions, which is really a very important concept. But there's also something which sometimes we will denote with big P, which is the statistical model. That's where I need really probability distribution. Okay, so in those statistical models, I usually made out of two things in the Bayesian decision framework. One of them is my prior distribution over the world state. I mean, whatever I think before seeing anything is my probability of any one of the world states. So this is a prior over omega. So this is some people don't really like the idea of prior, and they are called non-Bayesians. But for us, this is easy to think about having such a prior. How to choose this prior is a very tricky question. But we're going to see that eventually it's not going to be very important, especially when we talk about many observations. The prior is going to be less and less important. So we usually assume some naive prior, like half and half or whatever, if you talk about two things. And the other one, much more important, was what? The observation, the probability of the observation given omega. So this is the observation conditioned on the world. Or the probability of the observation condition. So this is the conditional probability, and these two things generate my statistical model. Okay. Any questions about it? It's really very simple. Okay. So now, what do I want to achieve? These are the formal components of what we call a Bayesian decision theory. And the first thing I need to say is, okay, what do I really want to know? So I want to get a decision. I want to get a decision. Maybe I should write it here. So a decision should tell me how to act in a given, with a given observation. Okay, this is, again, very intuitive. I see clouds in the morning. I want to know if to take an umbrella. So this should be a function from the observations to the actions. And this is what I call the strategy. So in principle, this is a simple, what we call strategy or deterministic decision. So it's a function. It selects one action per observation. But I said yesterday also that we may want to at least consider the possibility of making non-deterministic actions. So non-deterministic in this case means, okay, there's no one action that I select for the observation, but there may be a distribution of actions, for which I mean, okay, the action is now going to be also a random variable, and I denoted it by policy pi, which is essentially a probability distribution over actions conditioned on my observation. And I usually call this policy. There's no real reason for calling this policy and this strategy, but it's all right, policy. So this can be stochastic, which means it can be random, randomized decision. One of the first things I want you to prove is to show us if randomized decision really going to help us in this case, but that's okay, I'll keep it for later. Okay, so what we want to do is to define something which will help us generating. So this is the question, essentially. How do I find the optimal decision rule or the optimal strategy or policy? Okay? So what do you think? I mean, what should I do? So essentially, the world is unknown to us. Okay, the world is unknown to us. So I want to define something which is really what is the risk of any action like this. So something which we call the conditional risk. And these are terms, by the way, that are used by some other fields which are not exactly my field, like game theory or economy or things like this. Yeah, please go ahead. So a stochastic decision is what many of us actually do, even if they don't admit it. I look outside and say, okay, the chances of rain are more or less 50%. What should I do? Okay, so you flip a mental coin. I mean, if you don't do it exactly, well, when I say a mental coin, I mean, okay, you have a virtual coin in your head, and you say, okay, if you actually want to be very formal about it, let's actually flip a coin. Flip a coin and decide to take or not to take. I make a decision. I let the coin make the decision for me, okay? But, of course, it may or may not be a good idea. And sometimes it may actually help you.
You can move the stochastic decision process to one of your observations and then it becomes deterministic.
Okay, we'll talk about it in a second. Okay, exactly about that. I mean, do we really need stochastic? But in some cases, and we'll show it later in the course, despite what Amir says in his notes, in some cases we actually have, it's better to make the stochastic decision. I'll give you just one example. Imagine that you actually travel, sorry. Imagine that you're actually traveling on the road and you know that there are traffic jams. But you don't know exactly where they are. You just know that there's a lot of traffic. Now, if you just listen to your navigator, and you know that everybody has this navigator, and so they will all make the same turns based on the current knowledge, which means that they will all go into the same jam and create another jam. So actually, a better policy in this case is to actually randomize your actions a little bit, adding noise to decisions. Adding noise to a decision will spread the traffic along different routes. Not all of them will go exactly in this way, and this will actually save you time. So there are cases where the fact that you don't know things like where exactly are the other cars can push you to make randomized decisions. And so randomized decision can actually, in some cases, help. And of course, the other cases that it's actually very costly to know. So maybe I can take a satellite and take an aerial picture of the roads around me, which is exactly every car where it is and where it's going, such that I can calculate where I want to be in exactly half an hour from here. This is usually not the case. So we have lack of information. We have uncertainty. And in the cases of uncertainty or the case of costly information, it's really very expensive. And I'll be very formal about it later on. Random actions can actually help us. So in nature, we actually see a lot of stochastic decisions. And that's why I think that animals make stochastic decisions all the time. I think we make stochastic decisions all the time, which means that we flip mental coins or something like this. Okay? Yes. So the conditional risk is something which is supposed to be, and what is the expected risk of the action alpha with observation X. So how do I calculate it? What is my unknown here? So what I don't know is the actual state of the world. Okay, so what do I do? So this is a conditional expected risk. I average over the state of the world. So let's say that I know the state of the world. If I know the state of the world, the risk of this action, like this, the risk of this action at the state omega is this, okay? What is the probability of the state omega given X? Okay, so in principle, what I should do is simply multiply it by the probability of omega, if I know omega. So if X is going to determine omega, and it's going to be 1 omega, this is going to be the cost, okay? But since I don't know omega, I'm summing over all omega. Okay? So this is somehow a shorthand notation. So here it actually means sum over all the omegas in your world, or all the W's in your world, whatever you want to call it at this point. And what is this? This is the expected risk given X. I simply sum over all the omegas. And this is really the reason I usually do not use this notation. Sorry, this is lambda. Use this notation because then for some of you, this may look familiar. I mean, so this looks like a vector in this direction. This looks like a vector in this direction. So this is actually like a Bryant cat in physics, or like a matrix multiplication, if you want. So essentially, you can think about these as rows of a matrix, and these are columns of a matrix. So I can think about it as lambda multiplied by p in some sense. Okay, so it's a matrix multiplication, and this also, of course, is the expectation. So this is the expected risk, conditional or expected conditional risk. Okay. There's only one problem, one little problem with this. Yes.
Is this a scalar value or matrix value?
No, it's a scalar value. You're right. It's one row of this multiplied by this, but then I can turn it into a matrix.
Right, so it's an inner product.
So if this is a matrix with indices r and x, in principle, if x is discrete.
Right.
So this matrix R is simply this lambda multiplied by P as a matrix. So, but if you don't see it, it's not really important. If you program it in MATLAB, it's actually used to think about it as matrices, because then things become very simple. Matrices in MATLAB, as you know, are very easy to handle. So, but of course, it's a matrix, strictly speaking, only if both alpha and x are discrete and finite. Okay? Otherwise, we start to talk about infinite or continuous valued matrices, and this is a little bit scary at this point. But it's really not a big deal. Of course, if omega is continuous, by the way, usually what we mean is that there's an integral here. So the whole thing works for continuous distributions as well. This will be then a density, and this will be a differential cost. I mean, a cost at a given omega, and I have to integrate and multiply by the omega. But at this point, we think about everything as discrete. Okay? So there's only one little problem here, that I assume that I have this px given omega, and in order to do this average, I need p of omega given x. Somebody asked me yesterday, this is actually what you want, huh? P of omega given x. And of course, so how do we move from one to the other? Yeah. So we know, of course, based on Bayes' theorem, this is lambda of alpha given omega times what? P of omega, P of x, I'm sorry. Okay, P of x given omega times what? Times P of omega divided by P of x. What is P of x? No. So yeah, it's actually a normalization factor. I mean, it's the thing which will turn this into probability distribution. So you can actually write it explicitly. I didn't have it as part of my model, but it's actually here. It's written there. What is it? So P of x. I don't need it explicitly because it's the sum of all what? Over omega P of omega. Okay? So this is sometimes, usually we call it complete total probability theorem. I think that Noga used this term. So this is, by the way, true if what? What is assumed here? That's the omega disjoint and exhaustive in a sense that the union of all omegas is omega in some sense. So this is a complete set. So if I sum over all of them, I really get the true probability. Okay? Otherwise, I may miss something. So indeed, in our case, omega is just a partition of the state of the world into rain and no rain. Of course, you can say that the world is made out of many other things, not only rain and no rain, but the relevant part of the world for me is this partition. Rain or no rain, everything else, I don't care. I mean, it trace over, whatever. So, okay, so this is P of omega, and this is what we now then call the total probability theory. Okay. Now, notice that Bayes' rule has an interesting structure. and say something about it. So if you look at Bayes' rule, I think I'm moving way too slowly, but that's just the beginning of the course. So if you look at Bayes' rule, we can think about it like this: P of x over omega divided by P of x is P of omega over x divided by P of omega. This is actually a good way of remembering it. And this is something which I'll use again and again as a fundamental quantity. I mean, so it's the posterior divided by the prior. In both cases, it's equal. And essentially, what we just did here is we turned this into something which has the posterior prior of the observation instead of the posterior prior of the world itself. So Bayes is essentially this, Bayes' rule. But this is something which we'll see again and again. It's the beginning of a quantity that we later on called something like likelihood ratio. I mean, how likely is the state of the world omega after I see the observation relative to the likelihood it was before the observation? So this ratio is going to be 1 if the observation is independent from the state of the world. It's going to be something different from 1, either bigger than 1 or smaller than 1, if the observation actually tells me something new. So this is really something we call this the odds in the context of gambling, at least. And this is the thing that how likely something is going to happen if I know a little more. And you may see already, that this thing is going to be related to what I really learned, or what is the information that I gained from the observation X about W. Just this is a little note. Keep it here for a second, a few hours, let's say. A few lessons, I will come back to this. But it's already in Bayes' rule. So in some sense, of course, when I write it, I assume that none of these things is 0. I can divide easily, so I don't want 0 priors. It's not too good. And I don't want 0 probability of having X. If you have actually X that has a probability 0, ignore it. Take it out of your space. Okay? So essentially what we do here is we turn it into this odd ratio of the observation itself. All right, but now I'm in a position actually to make a decision. So this is a very good function, the conditional risk, with which we can actually evaluate a strategy. So what is a strategy? A strategy was a function delta of x. So how good? Evaluate it. So I now want to define something else, which is the expected or total risk. Given a strategy, so the total risk, so this was the conditional risk, or if you want conditional expected risk, the total risk of delta, of any decision rule that you choose, is going to be what? Again, I know it's extremely slow for some of you, but it's all right. So this is going to be some function of delta. I mean, when I write it like this, I usually mean that there's a function here, and this is a value of this whole function. And this is what we call functional. Okay, so I want to give a scalar, a number that evaluates the whole function as a function, not just one value of it. Okay? Is this something you... So in my standard notation, I usually try to keep it. Square brackets will mean functional. Okay? So what is this? So this should be, what would you, again, I want you to develop your intuition. What should be the expected risk? I mean, so this was conditioned on this at a given action. So now what I want to do is to take the conditional risk at the alpha, which is actually determined by this particular function. So, and condition on this x. So this will be implementing this strategy, okay? And then what I want to do is to average it over what? Over all x's. Okay, so I simply want to sum over all x's with respect to the probability of x of this. Okay, so this is the expected, sometimes we just write it like this, the expected over p of x, or sometimes we just omit it and write x, of the conditional risk of r of delta x at x. Okay, it's the same thing. Okay, so this is the total risk or the expected risk of delta. Notice that we have made a decision, just because it's easy to make this decision, that is the average, the expectation that we care about. This is not obvious at all, and it's actually sometimes not what we want. For example, we may want the worst possible risk. We may want to minimize the maximal possible risk, a min-max strategy, as we call it. This is actually, in many cases, is much more robust. I mean, I don't want to get to pay more than something, even in the worst case. So a good strategy, which is actually used in economy, in game theory all the time, I want to minimize the maximal possible risk. I want to be robust with respect. But here we are Bayesians, or we really like expectations. But remember that expectation only give us an average guarantee. Maybe in some cases we'll pay very high. Okay? So this is the expected risk or total expected on average with respect to this. Okay, so let's put this in some sort of a square. And now I have the first simple but something which you may call a theorem. What is the best possible strategy? Or which strategy actually minimizes the total risk? And what do you think? So again, I want a condition what is delta star that of x which will minimize, so I want to call it, just to introduce some notation that some of you know, of all possible strategies, all possible functions like this, which one is the one that minimizes the total risk? So this is my question. What do you think? Again, it's too slow. I just want to make sure that everybody is with me. So the theorem, if you want, despite the fact that it's actually very simple, it's actually important. So not all simple to prove theorems are unimportant. So the delta star, this best optimal strategy, or what we call optimal Bayesian strategy, Bayesian decision, is what? So the optimal decision rule is the one that simply minimizes what over alpha. By the way, argmin is known to everyone, because sometimes people have problems with it. Argmin is the argument that minimizes a function. Okay, it's the value of the argument. Okay, so in this case, this is a function of delta. It's the delta that minimizes r of delta. Okay, so argmin of what? Of the conditional risk. The optimal in the sense that, or this if you want, this decision minimizes r of delta. Okay, so this is called the Bayes optimal. This minimizes r of delta. Okay, so just usually these kind of things don't require proofs, but how do I prove it? I want to see a formal proof. Okay, so what is the proof? Anyone can just fill it for me. I mean, okay, so what do I do? So I just put the definition. I mean, so R of delta was this, is the expected over all, so P of x is given of R delta of x given x. This was the definition for any delta. But this is obviously, since R of delta is obviously larger, so this is greater or equal than the expectation of a P of x. I'm sorry, I don't need this. Expectation of a P of x of R delta B or delta star. Why? Why this is true? This is greater or equal. Why this is true? Because this was the minimum. This is the one that obtained, this is the one that really get the minimum risk. So this is always greater or equal than this. Otherwise it would not be the minimum. Okay, so this is about it. This is the proof. It's a black square. Okay. I know this was completely trivial to some of you, but I want everyone to understand the logic here. I mean, I just use the definition of minimum and show that I can minimize inside the expectation. So the one with minimized expectation is the function which is smaller at every point, and this is my. Okay, so let's move a little faster. Actually, I finished my first hour, so let's take a break. Any question about it? Any complaint about it? It was too slow. Okay, so you must help me tuning up the pace. If it's too fast or too slow, let me know. Okay? I'll go faster. Yeah.
דלתא כוכבית, לא צריך לרשום פה של x, זה כבר אומר לי מה הערך של דלתא, אני מחפש את הפונקציה עצמה.
אתה צודק, אני התכוונתי להדגיש את הפונקציה, אבל זה לא תלוי ב-x.
וגם פה אנחנו יכולים
לא, אני בכל זאת לכתוב את זה, אז שזה יהיה ברור שאני מתכוון כאן לכל הפונקציות, אבל זה פונקציה של x שלהם, זה לא מספר אחד.
לא ברור,
וגם זה פונקציה של x.
כן, אבל אתה מחפש את
זה פונקציה של x. אני יכול לכתוב פה x בכולם,
אבל אתה מחפש את
את כל
דלתא. לא את הדלתא של x.
לא,
אין פה x בכלל,
x הוא רק סימון שאומר שזה פונקציה.
כן. אוקיי, אז אתה אומר...
זה אומר שלכל x, זה כבר כן תלוי.
בדיוק, פה זה כבר כן תלוי. לא הבנתי,
אוקיי, שאלה טובה מאוד. זה לא מדויק שלי. אז פה x הוא קבוע. לא, לכל x אני מנסה את האלפא, אני עושה פעולה אחרת.
בדיוק, אני מזמן את אלפא ואני עושה
ל-x נתון, ב-x נתון. ופה אני אעשה את זה על פני פונקציה. כלומר, אני מקבל את זה לכל ה-x. מעבר לאקטיבה, לא מסוים, מה הבעיה?
אני רוצה פה הרבה דלתא. אני רוצה פה לכל x, אני מוצא דלתא. כל x הוא מוצא פונקציה.
נכון.
ואז אתה אומר, אני רוצה להציב את זה פה. אז אני כל פעם אני מכתיב, הרי פה אני רק על כל x, יש סכום על x.
נכון.
אז לכל x אני מכתיב את הדלתא
זה הממוצע על פני ה-x, לכל x אני
בכל x, תבחר את הפעולה של המדל הזה תמיד. אתה משנה את כל ה-x.
אז יש לי
לכל x תחשב את הדלטה שלו, את הדלטה של x שלו, את האלפא שלו. נכון? והפונקציה הזאת, המינימום, אז בוא נסתכל על זה. ההערה שלך לגמרי מוצדקת, מה שלא
יש דלטה כזאת?
זה הציר של x. לא. אז אני יכול לכתוב פה לכל דלטה בעולם, לכל אלפא בעולם, אני יכול לצייר את הפונקציה הזאת של x. זאת אומרת, בהינתן אלפא, אז זה אלפא 1 ומשהו כזה. לאלפא 2 זה משהו כזה. לאלפא 2 זה... אלפא 2 זה משהו כזה. נראה שיש רק 2 כזה. בנה שיש אפילו להוסיף, מצאתי את זה כאן. מה יהיה הדלטה האופטימלי? בכל מקום, פה אלפא 2 מה הוא יותר קטן. אז הדלטה האופטימלי נבחר את אלפא 2 פה. נבחר את אלפא 2 פה. אבל פה אלפא 1 הזה, נבחר את אלפא 1 פה. אני אעשה את כלומר, באזור הזה של ה-X'ים אני אבחר אלפא 2. באזור הזה של ה-X'ים אני אבחר אלפא 1. באזור הזה של ה-X'ים אני אבחר אפילו אלפא 2. הנה הפונקציה. אז זה עכשיו.
אבל הפונקציה הזאת,
הפונקציה הכחולה,
לא הייתה פונקציה שהייתה לי
למה היא לא הייתה לי? אני לא הגבלתי את הפונקציה. אני אמרתי כל פונקציה של X היא לגיטימית. אז בואו נבחר את זאת שבכל נקודה X ממזערת לי את הפונקציה.
כאילו, הבנתי. אתה שואל מה...
זה חשוב, אני עכשיו אסביר על זה כולם, זה חשוב.
אני לא צריך לבחור דלטה מתוך איזה שורות של דלתאות.
לא, ממש לא. כל פונקציה לגיטימית בעולם. אני צריך להגיד, אני גם מסמן להגיד. זה בעצם נותן לי decision region. אז פה תחליט אלפא 2, תרצה אלפא 2, פה תרצה אלפא 1, פה תרצה שוב אלפא 2. אני אגיד את זה במספיק, זה בדיוק מה שכמעתי להגיד, זה נקרא decision boundary, זה שוב שאלה מאוד טוב.
בעצם, אתה בעצם מחפש את הדלתא.
כן, זה הדבר הסוף יותר שאני יכול לעשות. לא יכול יותר. בכל מקום אני אעשה את הפעולה הכי מוצלחת. יכול להיות שהפונקציה הזאת מתורסת.
זו פשוט ההגדרה של הפונקציה.
נכון, זאת בדיוק ההגדרה של הפונקציה. אני רואה שיש כאן איזה בעיה עם הפורמליזציה. תסביר לך זה המחשב? אוקיי, אתה מאוד מקפיד על פורמליזם, זה קצין מגיע. זה טוב מאוד, אני לא פעם זה לא תמיד, כן, אפילו להעיר.
אני גם חושב שעדיף לא לרשום פה את העיר.
לא, אתה 100% צודק.
להגיד אולי במילים או להגיד...
אוקיי, אתה 100% צודק, זה כאילו חיה אחרת. אבל אז אתה יכול גם כבר לחשוב על זה כאוסף בפונקציה. רוב האנשים חושבים על פונקציה, אני לא חושבים על ה-F, אני חושבים על F של משהו.
אם אתה חושב על F של X, אז אולי אתה חושב
X מסוים. אז האמת היא שזה בעיה כללית. אתה אומר F של X. אתה חושב, בהינתן X מסוים, זה ה-F של X. אני חושב על זה כפונקציה של כל ה-X. כל ה-X'ים אפשריים.
אולי אפשר, מה שעושים הרבה פעמים זה רושמים F
X גדול, או נקודה. X גדול, זה יותר גדול. ואז נצטרך לשים את הפונקציה של סט. אני לא רוצה עכשיו לזה. אתה צודק. אתה יודע מה, בוא נתקשר על זה. אם על זה אתה מוכן להסכים. אני פשוט רוצה שתהיה ברור שזה פונקציה ולא סתם מספר. אוקיי? יופי.
right, I want to start again. So I continue. So in fact, thanks to David and probably some other courageous students, I realized that I was way too abstract, and or not formal enough, both probably. And of course, this thing calls for an example. And so what do we actually mean? So I want everybody to get in, and I'll explain it very, very slowly because it's really extremely important that you understand this all the way through, no doubts whatsoever. So first of all, the first comment of David was absolutely right. I was not very careful in my notation. I actually wrote here delta of x, and here minimum of a delta of x, and here x, or something like this, which some of you may think that I'm assuming certain x. But I'm not. I just want to emphasize the fact that this is the whole function. So David suggested that I immediately buy it, although I'm not sure I will use it all the time, to write just dot here. If I just write it delta without anything, you may think that I'm thinking about one value or something like this. So I want you to understand that this is the whole function for every possible x. Okay, so like this, you know that there's something here, I just don't fix it. Okay? Is this good for everyone? As a notation. Okay, then some people will keep me careful about the mathematical terminology, and that's really very important. It's just, usually I'm not going to be that careful about notations because I'm a physicist by training, but this is important. I mean, we tend to presume that you understand even if it's not explicit. Now here, of course, when I define the Bayes optimal rule, x is given. So this is for this x, any one of them. We always pick the minimum. Now this looks a bit strange. What I mean by this, so I it essentially takes the minimum value in all the possible functions. Actually, it sounds a little crazy. It's actually very simple, and so we drew here a little. So imagine that x is actually real, okay? Just because it's easier to write, to draw pictures with real functions, to me at least. So if this is x, let's say the real value between 0 and 1 or something, then the conditional risk is actually two functions of x. Let's say that there are only two alphas, okay? Only two actions, just to make things simple. So there is alpha 1 and alpha 2. Turn right or turn left, or take an umbrella or don't take an umbrella. Some of those binary actions, I actually elaborate on the binary actions immediately because it makes things simpler and easier to understand. So there are essentially, let's say there are two functions. One is the black one, which is the risk, the conditional risk as a function of x for a given alpha. So I put alpha 1 here, I get this function, and I put alpha 2 here, I get the red function. Okay? So what is this minimization? It means that every x select the lower one out of the one which minimizes the conditional risk. So at that x it will be the red one, at that x it will be the black one, and that x it will be the red one again, okay? So the function, this delta b of x, or the argmin, or the minimum, without the arg, the minimum of alpha of x is this blue function here. It's always the lower of the two, okay? Which means that I actually divided my observation space, x, in this case into three regions. Here you just take you do alpha 2, because here alpha 2 gives you a smaller risk. Here do alpha 1, and here do alpha 2 again. So essentially any decision rule like this is a partitioning of my space of observations into regions which tell me what is the decision in this region. So this is something called a decision boundary, or a decision region, or decision function. So delta of x is actually a partition, since delta was a function from the axis to the actions, from the observation to the actions. if the actions are discrete, like in this case, only two actions, it's actually going to divide my space of observations into two parts, where to disjoint sets, where to make the first decision and where to make the second decision. If you really want to be strict about it, and since there are people, you should tell me what to do here and here, where the two risks are equal. So this is what we call a measure zero set, so we don't care about it. But it's actually, you have to make some decision. Okay. So one way, take the first one, or throw a coin, or whatever you want. I mean, it's really not, doesn't matter. It's not going to change your conditional risk, because they're equal here. Okay. So, but you really want to choose an action. This is actually a good place to make a random decision. Doesn't really matter. Okay? Now, actually want to elaborate a little bit on this case of two hypotheses, or two world states. Okay, so let's make it a little even more explicit. So we want to say a little more about the case of both the world has only two values, especially like our example, I mean, like rain, no rain. The actions have only two values, like umbrella, no umbrella. And x at this point can be anything. So let's say that it's a real value, like the temperature, or something like this in the morning. So imagine that omega is made out of two omegas, omega 1. You know, I want to call it omega 0 and omega 1, because later on I'm going to call it hypothesis. And they usually call it, statisticians used to, it's going to be generalized immediately to what statisticians call hypothesis testing. And they use H0 and H1. And we call it omega 1 and omega 2. It's a bit confusing. So let's call them omega 0 and omega 1 at this point, okay? And so this is a binary world. And I assume that the action is only two actions, alpha 1 and alpha 2. If you want alpha 0 and alpha 1, doesn't matter. And x, let's say, some random variable belongs to the R. And now, even for simplicity, and this is something we may put in exercise more precisely, let's say that P of x in these two cases are Gaussian. Okay? So x is a real value is real, something like whatever, temperature, pressure, whatever you want. And we actually have two distributions. So this is the binary case. And lambda, in this case, is a matrix. Okay, so lambda is just a matrix. Lambda alpha 1 omega 0, lambda alpha 1 omega 1. It's a bit confusing. Lambda alpha 2 omega 0, lambda alpha 2 omega 1. You know, it's a bit, my choice of the indices here is a bit confusing, but never mind. But maybe call both of them 0 and 1, or 1 and 2, but never mind. So this is the matrix, the 2 by 2 matrix, okay? 4 numbers. You can actually make them, so this is the matrix, lambda ij alpha I omega g. And let's assume that these two things, so there's some prior distribution, just for simplicity, so there's P0 of omega 1, P0 of omega 0, and so on. This is the prior of the two states of the world, which for simplicity we'll assume to be equal now. Actually, I'll show you immediately that if you have making many observations, this assumption doesn't really matter much. And we assume that we have P of x given omega, any one of them is a Gaussian. Okay? So what do I mean by this? Normal distribution. So what do you know about normal distribution? So x I assume to be real. So normal distributions are characterized by what? Two numbers over the real numbers, or in one dimension. The mean and variance, or the mean and standard deviation. Okay, so let's say that we have mu1 and sigma 1, and just denote it by a blue curve. So it has a nice Gaussian distribution centered around mu1. I know that's not, and has a width. So you know what the variance is, or the square root of the variance is what we call the standard deviation, which is essentially the width of this function at the value 1 over e away from the center. Not really. I mean, okay. So this is sigma, which is the square root of the variance. Okay. So in principle, this goes forever, but it goes very quickly, like e to the minus x square, more or less. So it's x minus mu square. So this is just to make sure that you know what I'm talking about. It's 1 over square root of 2 pi sigma e to the minus x minus mu square over 2 sigma square. Okay, so when x minus mu is sigma, that means sigma away from mu, plus or minus sigma away from mu, this will be just e to the minus half. Okay? So it will go like e to the minus half now. Okay, so this essentially determines this point. And this is just normalization. So I'm sure you all know where it came from. And if you don't, remind yourself, where's this 2 pi coming from? Huh? It's a bit funny, but it's actually very good to remind yourself. So this is 1. So let's say that this is px given omega 0, and there's another one. And let's say that the other one is centered here, mu1, mu2, and has a variance sigma 2. So let's say that it's a much wider Gaussian, that sigma 2 is much larger. It's really bad. Okay, so sigma 2. So this is sigma 2 and mu 2. So let's say that it looks something like this. It's supposed to be a wider Gaussian around this point. I'm sorry, my drawing is really terrible. Okay, but you know what I mean? Okay, this has it's a much larger sigma. So these are, for example, two conditional distributions like this. This is px0, and this will be px given omega 1. Okay? So now, and let's say, just for simplicity, that my error function is very simple. Okay, actually, before doing that, keep this in mind for a second. If I want to assume that the priors are equal, then it will make my life a lot easier. But essentially, I want to see what is the meaning of this decision rule, the Bayesian optimum. So in this case, the decision boundaries are going to be determined. I mean, these places where I actually change my decision are going to be determined by these two functions. R alpha x1 equals R alpha x. So essentially, the decision boundary, where am I going to decide? I now want to see where do I have to partition x, just like in my little example here. Where are these boundaries? So where are these boundaries here? What's determined them? This is precisely the points where R alpha 1x equals R alpha 2x. Okay? These 2 points. Precisely where the two risks are equal, these are where my decision boundaries are. Is this clear? No. Look at you. So essentially, I'm telling you this is the arg minimum. I want to know where are those flips. So when the minimum goes from one to the other, at that point they're equal, okay? So this equation, R alpha 1x equals R alpha 2x, determines the condition, the decision boundaries, where I'm flipping my decision. This should again be clear to everyone. If it's not clear to everyone, I'm too abstract. So I just want to see my decision boundaries in this case. So the decision boundary is determined by these two equations. In this case, R alpha 1x equal R alpha 2x. Okay, but what is this? What is R alpha 1 and R alpha 2? So in this case, R alpha 1 is precisely this sum. Okay, so I'm writing it this way. I can essentially keep the Bayesian term there. So R alpha 1x and R alpha 2x are going to be determined. Well, if you do this exercise, so sum over omega of lambda alpha omega p omega alpha 1 of omega p omega given x must be equal to sum over omega alpha 2 omega of p omega given x. So if you just play the exercise here and see this in this two-dimensional case, you get the following equation, which I want to write somewhere. Okay. Equate these two conditional rifts. And what it leads to is the following equation. I just wanted to write it down. It's R p of x over omega 1 divided by p of x over omega 2 is less or equal, this is my decision rule, p of omega 2 over p of omega 1 times something which depends only on the two costs. I mean, okay, essentially what I do here is break this sum into two terms, break this sum into two terms, and put together the things that multiply the first probability, and put together the things that multiply the second probability, and I get precisely this. This ratio, lambda of alpha 1 omega 1 minus lambda of alpha 2 omega 2. So I see that I already switched here from 0, 1 to never mind that. And divided by lambda of alpha 1 alpha 2 omega 1 minus lambda of alpha 1 omega 1. So this is 2. So essentially my decision rule is this. The equality, when they're equal, it's precisely the boundaries. So here I actually tell you a little more. Decide omega 1 if this is greater than this. Decide omega 2 if this is less than this. Okay, so I get, if you are not sure, just do the algebra. Essentially what you do here is there are two terms here, two terms here. One of them multiply p omega 1 x. The other one is p omega 2x. I just bring them together, put them on the other side. I know this is a little, it's not clear, but it's really easy to check. Check this. Okay, it's simply algebra from that equation. So the same boundary is actually determined by this. I decide alpha 1 if this is greater than this. I decide alpha 2 if this is greater than this. So you could call it less or equal. The boundary is the equality. Maybe I should write equality here. Now notice one very interesting thing. So essentially I can bring to one side the things that depend on x. And the other side, the right-hand side in this case, is independent of x. I mean, is there anyone here who doesn't know how to go from this to this? In principle? I should do it more slowly, but essentially, as I said, I mean, this is two terms. I really should write it down. lambda alpha 1 omega 1 p omega 1 x plus lambda alpha 1 omega 2 p omega 2x, and the same is here. And now I simply change the order. I bring all the p's to one side and the other p's to the other side and divide, such that I get here this ratio. This depends on x, so this is going to determine my boundary. This is independent of x. It depends only on the priors and on the costs. So here you get actually a very interesting lesson already, and that the boundary, the term that depends on x it always has the form of some sort of a ratio of two probabilities. And there's a threshold here. There's some value that depends only on the costs and the priors. Okay, so this is something which will seem to be much more generally true in the next hour when I prove the Neyman-Pearson theorem. But this is called, in our notation, is the likelihood of x at omega 1 divided by the probability of x divided by omega 2. So this is called in the statistical literature the likelihood ratio. Likelihood ratio is a very important concept. You'll see it again and again. It's what is the ratio between these two probabilities. Okay, so which one is more likely? And this is some sort of a threshold function. It's a constant number for a given, for any x. As a function of x, it's constant. Okay, it's independent of x. So essentially what the decision rule looks like is compare the likelihood ratio to some constant. Okay? Okay, so now let's just assume for a second this constant is simply 1. When will it be? If this price difference, this cost difference function is precisely 1 over the priors, or if the priors are equal and these are the same. And one very important case like this is precisely when I want to actually decide according to my error. Let's say my cost is the probability of making an error. And I'll get to this in 1 second. But even before doing this, essentially what it means, I have to look at the ratio of these two functions. So the likelihood ratio is the ratio of these two density functions or probability functions. So you see here, I actually move to density functions without saying anything. Why is this still true? I mean, everything as I said still works for density functions. I mean, I move from probability to density freely. Think about it. Is it really allowed? Of course, it's allowed because essentially moving to probabilities again, what really means, I'm going to say it only once, is really to divide this space into many, many small intervals, delta x each. And if I just divide this place into delta x, let's say delta x is epsilon, something very small. And then for each value of x within epsilon, the ratio multiplied by epsilon are the ratios of probabilities. Okay, so this is true for any epsilon in some sense, or for small enough epsilon, it's certainly true. So I can really move from histograms like this, in discretized epsilon, which in that case it was all probabilities, everything is valid and kosher, to these functions without really cheating you, because epsilon simply goes away. So if I take the likelihood ratio, the likelihood ratios of probabilities are exactly the same as the likelihood ratio of densities. It has exactly the same meaning. If you think about this, I multiply by some delta x, and this is multiplied by delta x, but the delta x simply goes away. Okay. So in this case, it's perfectly valid to think about densities. So let's say that this constant, just for the simplicity, and I'll come back to this in a second, is 1. So if this is 1, what is the boundary region here? So again, it's exactly where the ratio changed from smaller than 1 to larger than 1, or where they're equal. So in this case, the region, the boundary decision, is going to be precisely where these two Gaussians cross each other. And notice that even with two simple Gaussians, if the variance is not the same, we already get 3 regions. Here decide blue, which means omega 0, omega 1. Here decide red, and here decide blue again. actually, yeah, because I'm talking about cost, so the probability of this is costly. Anyway, it's likelihood ratio compared to some threshold, which is independent of x. Now there's a one, so as I said, I mean, there's a specially interesting case, which is extremely important. The risk is the probability of error. Probability of error is something which we really care very much about. Let's say you're making a decision on something like a disease. I mean, so a very simple decision like this can be measure your temperature in the morning and decide if you are ill or healthy. Okay? Or something like this. You're making a medical diagnostic. So or given a medicine based on some observation and so on, this type of decisions are always important. I mean, that's why medicines are very important. And really what eventually tells us everything we want to know is what is the probability that we actually made the wrong decision. So now if I want the probability of error, what should be the lambda? What do you think? So essentially in this case, I'll tell it to you, some lambda ij, if there are two hypotheses, in this case lambda ij is simply what? So if I'm, so probability of error means that alpha, the action, is just deciding on omega. So let's say alpha 1 in this case is deciding that we are omega 0, and alpha 2 in this case is deciding that we are omega 1. Okay? So alpha is just decision what is. So it's really very simple. Our umbrella rain experiment is precisely like this. You want to decide if it's going to rain or not. The fact that I have to carry an umbrella is really irrelevant. The decision is really, is there a rain or not? And I want to minimize my probability of making a wrong decision. So in this case, what is alpha? So again, for some of you, it may be trivial. It's 1 minus delta ij, where delta ij is what? Is the Kronecker delta. Delta ij in this case is 1 when I equals j, and 0 when I different from j. Okay? So verify to yourself. Here I'm going to pay a price if I decided on the wrong thing. Okay, so it's going to be 1 if I is different from j, which means I decided alpha wrong, different from omega. So I decided rain, it was actually not raining. It's going to be 1 again if I decided not raining, it was raining. If I decide the correct one, if I equals j, my decision was right, it's going to be 0. Okay, so this is really a cost function. So it's very clear that in this case, if the risk is this, if the cost is this, the conditional risk is going to be the probability of error with this observation. So probability of error is a very important concept, and I actually want you to notice that there are really, in this case, two probabilities of error. So what are the two probabilities of error here? One of them is decide 1 and or falsely, I mean, in the sense that you decide 1, it was actually 2. And the other one is decide 2, and it was actually 1. There are two different types of error. One of them is what you usually call the false rejection, or first type of error. The other one is false acceptance. And when we talk about hypothesis testing, we actually call this accepting the hypothesis falsely or rejecting the hypothesis falsely. They are not necessarily the same. So let's look again at my Gaussians here. What do you think are the probability of errors? So when, just from looking at these two densities, so if I take this to be my cost function, it's really easy to see that the risk, the conditional risk, is simply the probability of making a wrong decision. This is the conditional risk. I have to verify that. But if I just look at these two Gaussians, what is going to be my decision, my error? Okay, so let's just complete the Gaussians to make sure that you understand that there are integrals, they have tails all over the place. What is the probability of error from this picture? Look, it's actually a little tricky. So let's think first about, I decided blue here, but this was actually, I decided red here, but it's actually blue. So what is the probability of this to happen? What is it? So let's say in this region. In this region, I decide red, but there's still a small probability by this blue tail that it was actually blue. So I made a wrong decision. What is the total probability of having it blue?
1 minus.
So yeah, so in this case, it's actually really 1 minus. I have to do it maybe more carefully, but you'll see that this is just the error, the area under the blue curve. From the black line. Yeah. Well, yeah. Okay. If this is really the decision boundary, this is the error. Yeah. And in this case, let's say I decided the blue again, so it's going to be the sum of these two things. One error in this is this, and the other one is this. Essentially, it's the remaining probability in the decision region that you decide something of the other hypothesis. So I decided that it's okay. So this is something you're going to play with a lot more and make sure of that. But maybe I should complete the holes in my argument here. So why is this function giving you the probability of error? So the easiest way to see it is simply look again at the definition of the conditional risk. Let's say here. I plug here lambda 1 minus delta, which means I sum exactly on the cases over the axis for which I make the wrong decision, because the other one is 0. And then the sum over all the states of the world, or all the observations in this case, is simply going to give me the integral over all x's for which my decision is opposite than what I need. And this is precisely, in this case, the probability of error.
What does the I and J stand for?
So I and J, remember, we're talking about binary decisions. So I and J are the two alphas and the two omegas. Okay? So I and J in this case are 1 and 0 and 0, 1. I mean the two possible states of the world and the two possible actions. Okay? So it's a matrix. In this case, it's a 2 by 2 matrix, delta ij. So this is simply the matrix 0, 1, 1, 0. Okay? 1 minus delta. Delta is the diagonal matrix. 1, 1. 1 minus delta is this off-diagonal 1. Okay? So essentially, this matrix is going to make sure that my total error, total risk, is really the total risk in this case is the average of all x's, is simply the sum of the two errors. This has to be done a little more in more details, but that's it. I feel a little uneasy about the way it is described here, but so essentially I get the probability of the tails to be the probability of error. Actually, in this case, here I decide, let's say, blue, and the probability of error in this case is actually quite large. And the area of the red curve in this region is this. So in this particular case, there's quite a big probability of error here. So again, a much more a reasonable decision boundary, something like this, where the two Gaussians look similar. And again, let's say that this is my decision in this case. There's only one point where they're equal. And in this case, the probabilities of error are simply going to be the probability. This is P of x given omega 1, and this is P of x given omega 2. And so in this case, again, this simple decision is going to decide 1 here, because here it's more likely to be omega 1, and decide 2 here, and the probability of error is simply going to be these two tails. The probability is I make a decision of omega 1 here, but it was actually omega 2. Or the probability that I make a decision omega 2 here, and it was actually omega 1. So the two types of error are going to be related simply to the tail here and the tail here. I just wanted, this example is much more complicated, but this can actually happen with Gaussian. Yes.
So the ratio, if the ratio is not 1, it's something larger than 1, then that means that one probability can be higher, but still I should choose the other one?
Yes. Okay, so when can the ratio be different than 1? Okay, either, let's say the prices are again 1 or 0, just like here, so this is the same. This doesn't going to change much. But if the priors are different, so your evidence, you're going to move the threshold according to the prior ratio. So let's say that the P omega 2 is twice more likely originally than P omega 1. This is going to be 2. Okay? This is going to be 2, means that I'm not looking for the places where they're equal, but where this is twice than this. This is twice than this. In this case, it's here, okay? Or something like this, okay? And twice than this here. So it's actually going to move the threshold to the place where the ratio is different than 1, okay? But in principle, it's exactly the same game. I mean, so just moving it to another ratio, another value. If the cost ratio is different than 1, then again, the same phenomenon. This is just going to shift the decision boundaries according to the ratio of priors and costs. Okay? Yes? So the threshold is this value. It's a constant. I call it a threshold because essentially what it tells you, that the decision rule in this case, is look at the likelihood ratio and compare it to a threshold. So something which is independent of x. What determines the value of this threshold are these two things: the prior ratio and the cost matrix. So this is a function which is determined by these two things, and we'll see later on boundary. You'll see later on that this is a much more general statement. I mean, comparing the likelihood ratio to a threshold is in general the best thing you can do. And this we'll see in the next hour, in the next lecture, which is something called the Neyman-Pearson lemma. Yes?
The probability of error is independent of the observation itself?
No, of course, the probability of error is determined only by the model. I mean, the probability distributions and the prices and priors. So essentially, it's determined by these two functions. And where do you put the threshold? Okay, so essentially, no, it's independent of the observation. It depends on the model. That's a very good point, because it seems like, okay, if there's only one observation, then I'm bound to have some error. Yeah, okay, so in this case, for example, this is the best I can do, comparing it to this threshold, but there's a probability of making a wrong decision, because it may be that the state of the world is different than what I think. I think it is this, but it's actually this. So these two tails in the integral of the Gaussian from here on, and the integral of the Gaussian from these two tails these two tails of the Gaussians are going to determine the error independent of x. It's a probability of error. Now, when actually I see x, I may be anywhere on this curve, but this is a priori the probability of error. So you see that minimizing the conditional risk, or minimize the total risk, in this case, it's going to be exactly minimizing the sum of errors. In this simple case, I give the same cost to errors of the two types. So making an error is simply cost me 1. It doesn't matter which type of error. I'm giving the same cost 1 to making an error, and cost 0 to not making an error. And in this case, the total risk, the conditional risk, is simply the probability of error. And the total risk in this case is going to be the sum of the two errors if the priors are equal. You actually we're going to do an exercise about it, so I hope that by then it will be clearer. So I just want to. Is there any question about it?
Can you repeat the point that he made? It doesn't depend on x?
No, you see that I could calculate the probability of error from two things. It's the area under the curve of two functions. Both of them depend only on the two distributions, on these two condition distributions. X is integrated. So it's determined by two things. What are the two functions? And where do I put the threshold? Okay? So if I put the threshold here, it will have a larger error here and a smaller error here, but it's not optimal. The optimal one is precisely the one which minimizes the sum of the two areas. Okay, and you can see here very easily that the sum of the two areas in Gaussian, in this case, is going to be minimized if I put it here and not here. But it's not clear. I mean, that's going to minimize the condition, the total risk in this case. So it's independent of what X was. It's a function of the distributions of X on the state of the world and the cost function and the priors, which is going to determine this threshold. Where do I put the boundary? Somehow I feel that the whole thing was a little messy, but I hope you'll get it eventually. It's really not hard, but it's actually a very important concept. So what should I do? I mean, it seems that the probability of error is doomed. I mean, is there any way to improve the error? What do you think? Let's say with this exactly the same setting, I'm having a single observation, the distributions are given, and I want smaller error. Can I actually get around it? Yeah, you want to somehow separate them more, but you can't. This is the world. So what should I do? What do you think? Again, guess. I need more data. That's essentially the answer. I mean, so let's say looking at the clouds in the morning and deciding if it's going to rain or not is simply not enough to make a good decision. From this, I can always have an error, let's say 30% error that I'm doomed to have on average. So, of course, what you should have said, and you eventually will say, the only way of improving error is to have more data. Data is so what I mean by more data. Let's say more observations. I open the radio. I look at the forecast on my telephone. Who said it yesterday? I'll do other things. I mean, I look for more sources of data. Okay. So the next thing we want to discuss, and in some detail, is optimal decisions, but not from single observations, but from many observations. So let's look at it for a second at this particular equation. Okay, so essentially in this two class decision boundary, I can write this as some sort of a theta. The threshold is independent of X, no matter how I make it. I mean, may or may not depend on the prior, and this is simply the likelihood ratio. Essentially, everything is going to be determined by the likelihood ratio. So let's say that I have many observations, a sequence of observations. And you see immediately why the likelihood ratio is so important. So I have 2 minutes just to write this down. This is going to be the main topic of the next lesson, many observations. So let's say that X is actually a vector, X1, X2, up to Xn, n observations. And let's say that I actually make them, so I actually denote this one by Xn, which means n observations. Okay, so this is just a notation. I have a vector of observations. And to make life easier, we assume that these are independent observations taken from the same distribution. So each of these xi is distributed from px given omega, IID. Again, what do I mean by IID? Independent, identically distributed, which means this is really very, very important. Remember it again and again. Each of these observations is taken independently